So let us take a look at example 1. You have circular cylinder of mass m and radius r. So we have radius r here connected to a spring modulus k. So if it is free to roll on the rough horizontal surface without slipping. So we want to find its natural frequency using Lagrange equations. So here you have to identify, okay, if you look at the element, you have here you have your cylinder, which you have J, M, okay, and also you have K, the spring. So it's actually the cylinder and the spring. So this thing is also rotating. So if you write your Lagrange equations, so let me put back the Lagrange equation here. So basically, if you look at this system, okay, you do not have any damper. So your C here is 0. So that means your D is equals to 0. Means no Rayleigh dissipation function. You just have the cylinder which has J, M, and then you have your K. So that's why in this equation, so when you look at this equation, the D expression gone, is D is equal to 0. So that's why you have this simplified version of the D is 0. So you look at, there is a kinematics that you have to consider here of between X and theta, because you have a linear spring here, okay, if you look at it clearly. So basically, if you if I want to draw, this linear spring will experience X. So whatever, maybe here will be clearer, okay. Whenever you have your angle, okay, here is X, and this is angle theta, and this is R, radius, yeah. So based on the kinematics, you have this X and theta and R. So your X is equals to R theta. Okay. So that's the relationship between the displacement of your K and also your X here. So that's why when you actually express in terms of theta, so your theta is equals to X over R. Same as your theta dot. Okay. So when you want to write your kinetic energy, so remember the cylinder has two things here. You have it in the expressions in terms of J as well as in terms of M. So if you put the kinetic energy for the J, because this thing is rotating, so the equation is half J theta dot naught, okay. And in terms of M is half mx dot naught. So you're done with the kinetic energy. Then you just rearrange the terms. Okay. So you can see here, we want to express everything in terms of x. So we change your theta in terms of, you have your j value here, have mr squared, and your theta is in terms of x. Already, as what we defined just now. Your theta is theta dot is equal to x dot over r. So you can easily then rearrange and factor out, then collect the terms in terms of x dot. So you've done with kinetic energy. Then you look at your potential energy, because there are only two. Remember, there are only two. One is the kinetic energy from the J and the M. And the second one is from the K. So the K, the potential energy is half kx squared. So then after that, you can easily substitute into the equation. So let me just bring the general equation just now. This is the general equation. So you can see that this is your T. Basically, this is your T. And you don't have D, so your D is equal to 0, and your V, so this is actually your V. Okay, so it's just a matter of substituting, and your Q here, Q1 is equals to x dot, Q1 dot equals to x dot, and your Q1 here is equals to x, as I mentioned earlier. So what you need to do is just take the partial derivative here. So easy. So 2 times 3 to the 4 mx dot. Same here. If you look at here, this is x dot. So basically this term is going to go to 0 because there's no x term here. It's just x dot. Yeah, you have to look for x. So that term is 0. And this is easy. 2 times half kx. So that's how you get this equation basically. Yeah. So from here you get this expression, and you can rearrange the terms. So you can see that if you are asked to find the undamped natural frequency, this is actually your EOM. Okay, so you can rearrange in this form, okay, which is quite similar form to your theta double dot plus omega n square. Okay, omega n square x equals to 0. This is the general form. So whatever coefficient here is basically your omega n square. So to get omega n, you just take the square root of that. Now let us take a look at the second example. Is when you have a uniform rod. Okay, so you do have mass freely pivoted at point O. So this is point O, your pivot point. So you assume small oscillations. So this makes sure that we can use the equation of your displacement, because your C and your K are linear. So in this case, you can already see that you're gonna get a kinematics between the displacement of C and K in terms of x is basically is gonna be either A or B. Yeah, A for C it will be A theta. Yeah, for K will be B theta. Okay, so what you want to find here, the undamped natural frequency and damping ratio, but you want to use Lagrange. So basically Lagrange is to get the EOM. From there you can extract parameters. So in this case it's still the same. You use the Lagrange equation. So now we are using full, because now you have D value, because you have damper. So as I said, you have a displacement for spring as B theta, and for your damper is A theta dot. So as I said, this is from this equation. So maybe I put if I put X here for the C. Okay, so for the K is basically from the pivot point O. You can actually draw a small triangle here just to depict your theta, your B, and your X for K here for spring. If I call X spring and this one X for C, yeah. So this is point O here. Okay, so basically your XS is equals to B theta. So we have defined it here. So then you can also find that the mass moment of inertia is given by these expressions. You can actually derive it, okay, but now it's given. Then you have the kinetic energy of the rod. So it's actually have a J naught theta dot. So you can just substitute what is the J naught here, okay, and simplify that, and you have the Rayleigh's dissipation function. So basically you write down all the kinetic energy, what is your Rayleigh's dissipation function, okay, in terms of the values that we have expressed. This is the general equation. XD, we already converted into theta. So XD is equals to A theta just now, A theta dot. So that's how we get the expressions. And the potential energy have kx squared, we have to write in terms of B theta. Then we insert into these formulas. So this is your kinetic energy, this is your dissipation energy, and this is your potential energy. So you can see normally this term will always go to 0 normally because there's no theta here. Okay, there's no theta there. Okay, so then we just differentiate. So once you get that, you differentiate, then you get the EOM here. So rearrange such that you have it in this form, or it's very similar form as theta double dot plus 2 zeta omega n theta dot plus omega n square theta. So this is the generic form. So you can match up all the coefficients as an equivalent values to get all the parameters, because you want omega n and also your zeta. So from there you can see you get your omega n, okay, from the expressions. Okay, and you can also get your 2 zeta omega n here is equals to 3Ca mb square. So that's how you get these expressions. Okay, so from there you can calculate your zeta, then this is the answer. Okay, we're done with example 2. Then we move on to the second part, which is the 2 degrees of freedom system. I've mentioned earlier, if you have 2 degree of freedom system, then you would need to have 2 equations. So you have to do it one by one with respect to each of the variable Q1 and Q2. So the equations are still similar for T, D, and V, very similar. It's just now you have to differentiate according to the generalized coordinates Q1 and Q2. Okay, don't worry about all this mess here, because if you written in variables, maybe it's difficult to understand. Maybe we can also take a look at the example. So this is how it looks like, because in 2 degrees of freedom system, you may want to write it in matrix form. Your EOM will be in matrix form. We go straight to the example, so it'll be easy for you. So we want to use Lagrange equations to do this. Normally in to derive equation of motions, you do need to draw the free body diagram for if you're using Newton's second law, but in Lagrange equations, you just identify the elements. So basically the keyword here, you have to identify the K and the C, yeah, and the M, basically all the elements, and see how you can actually express each of it in terms of energy. So this is the Lagrange equation. So you can see here there is no C is equal to 0, so you don't have D expression. So you only have T and potential, kinetic and potential energy. So you just identify what is the kinetic energy. What do you look for? Basically you look for the mass and the J, okay, the M and the J. So in this case you have both. For the rigid bar, so you have the rigid bar will actually move in the x direction as well as theta. So it has both M and J. Okay, and then for the potential is the tricky part, because in this case, for the potential you would need to determine the what we call relative displacement. Okay. So you have to consider kinetic potential energy with respect to translational displacement. So you have to decide on the plus and minus here. So let me just show you very quick. I think this is actually revision on how you determine the relative displacement for K1 and K2. In here, it's already given x is going up. So I'm drawing K1 goes up and K2 goes up, so that you get positive x. Okay, both are positive. Then you only determine what is the direction from point, from the pivot point. So this is actually the pivot point. Okay, so so assuming your pivot point is there, and you just look at the arrowhead. If you look at the arrowhead, from this arrowhead to this arrow, So it goes like that. We already have, sorry, I forgot to say this. In this case, we have to follow the questions. Counterclockwise is positive. Yeah. So this one goes up is positive. So that's the designation that we assume based on the question. So if you look at again, okay, let me erase this. So if you look at from this pivot point to this arrowhead, it's like that, isn't it? So you are actually going clockwise. So if you go clockwise, that means it's negative. So the way to write it, the distance from here to here is L1. So you have L1 theta. So here, the negative is L1 theta. So the way you write this force is K1 x minus L1 theta. Then you do the same thing for this one. Maybe I use a slightly different color here. For K2. So for K2, you do the same thing. If you look at this arrowhead, okay, you go from this point to this arrowhead. It goes like this, yeah? So when it goes like that, so that means it's actually, or I can say it goes like this as well, because it's a circle, isn't it? It goes like this. So it's actually at clockwise. So it will be positive. So maybe I undo that so that it will be easier for you to look at it. So from this arrowhead to this point, isn't it? So then you know that it's according to the counterclockwise, so you get positive theta. Or for K2, the positive is actually this distance here, okay, to K2 is L2 from the pivot point, isn't it? So you would have to write L2 theta. So the positive part is actually L2 theta. It's supposed to be capital L, yeah? This one, capital L. So then you can write your K2 here is basically the force here is K2, both are positive, x plus L2 theta. And this one is K1 x minus L1 theta. So basically we just want to determine the direction. So if we go back and continue to the slides 35 here, so you can see that is how we got these expressions. Okay, remember in the question they already mentioned about small displacement. Okay, so when you talk about small displacement, then your sine theta is equals to theta. So that is in most or throughout these courses we have this assumption. So that's why you end up with L1 sine theta is basically L1 theta. Okay, so instead of just writing kx squared, so now we have it in terms of relative displacement, okay, for both sides, which we derive it from this method of determining the relative displacement. Then we can go ahead and rewrite the equation of motion. We take the partial derivative and we can write the equation of motion. Okay, if you do that, okay, you can see now they already replace it. So as what we had in the previous expressions, you don't have any sign notation before. So if you substitute into your list of equations, you have just now your t. Okay, you have your t expression. So you substitute into these two. One with respect, basically you have to differentiate with respect to x. Another one with respects to x dot and x. Another equation is with respect to the theta dot and theta. So that's what we do here. So we already have expressions for kinetic energy and we have expressions for the potential energy here. this one with respect to x and this one with respect to theta. Then you can actually substitute into this first equation and the second equation. So this one with respect to x, this one with respect to theta. Okay, so you have this expression, then you can write it in terms of matrix. For example 4, okay, this is another system where it's actually a combination of a mass and also a roller here. So from these expressions, you also from this system you also identify the masses. So you can see M1, mass 1 here, but for this cylinder, or basically a circular cylinder, you have two, M2 and J0. Okay, and this one moves at x, M1 moves at x, whereas this one moves at theta. So you also have two variables here. You have to express one with respect to x dot and x. Another equation is with respect to theta dot and x. Okay, so basically these are the definitions of your Q1 and Q2. Okay, same as your Q dot 1 and Q dot 2. Okay, since here they do have C, K, M, so they have all the three elements. So that's why you are going to use all the energy here. Yeah? You have the expressions. So you have 6 expressions basically there. So let us take a look at kinetic energy. So as we have seen, we have M1 and J0 there. Okay, and then we also have, okay, for your information, this system is slightly different than the previous one. You do not have, the M does not move at X, but it has a J here because it's rotating. Yeah? And it also has external moment and external force. So make sure you don't miss that out. So that's why for kinetic energy, you just have the mass from M1 and then J0. Okay. Then from the Rayleigh's dissipation function, if you look at again this one, you have C1 and C2. So now you just identify all the elements. So for Rayleigh's dissipation function, you have C1 and C2. And then for the potential energy, okay, take a look at it back. You have K1 and K2. So you write for K1 and K2. Okay, so just take note, for this Rayleigh dissipation function and potential energy, you do have this expression, which is also the relative displacement, x minus r theta and x. So let us continue. So basically, how do we actually draw the determine the relative displacement for K2 and C2? Okay, basically for K2 and C2, you can see that here. Maybe I highlight it again. It's in between x and also theta here. K2 is located in between these two. So because I want x to be positive, so it's easy for me. X going to the right is positive, so that's why I have this arrowhead here to the right, so that I have positive x for both K2 and C2. So for this element, if this one goes to the right, this one has to go to the left. That is the rule that you cannot break. It means that K2 and C2, to get plus x here, K2 and C2 has to be in compression. So this one has to go to the left. Okay. So if you do that automatically, then because it cannot be both to the right, so one has to be to the left, one has to be to the right. So then you refer this direction of these arrows to the direction of the theta. So you can see the theta, clockwise is positive here. So if you look at this arrowhead, okay, maybe I do that. Okay, if you look at the arrowhead from the point of rotation, so maybe I take this is actually the point of rotation, then you go there like that. So this is the arrowhead or the direction of it. So it's opposite. So both are counterclockwise, isn't it? So both are counterclockwise. So that is why you get negative theta here. Negative theta. This one also negative theta. So the way you write K2, maybe I make it very clear here then. So the way you write your K2 force here should be X. Okay, instead of just minus theta, you have to look at the distance here, which is R. Okay, so that's why K2X minus R theta, same as C2. So the way you write it is C2X minus R theta. It should be dot, yeah? So that is how you determine the relative displacement. So we go back to the solutions for the example 4 just now, which is this one. So that is how you get these expressions, okay, for your X minus R theta and X minus. So basically from these two expressions that we have derived, okay. Then you actually substitute. So for the kinetic energy, now you have to do, you can also do, this is another way of doing it, column by column. So you can make a column. So this, all these with respect to X and X dot, okay, and this one is for theta and theta dot, okay, the right side of it. So then you solve each of it. So you can see the kinetic expression equation is still the same. What's the main difference is the variables that you use for the partial derivative. That's all. Sorry, not that one, but this one. Okay. So those are the main difference. So you would have slightly different expressions for those. Then do the same thing for D. So this one, when you look at it with respect to X dot, this one with respect to theta dot. Then do the same thing for potential energy with respect to X and theta. So you may want to have these two columns, okay. You can also see here is always, this expression is always 0. Most of the time you can see that it's always 0. Okay, so you have all these three expressions. Then you collect all the terms and substitute back into the equation. So if you do that, you have this as the first equation. So remember just now we have the force input as also moment. So don't forget to put the input there. So you finally get the matrix form. Okay, that's all. So easy peasy. It's just substituting. So the main steps will be identifying the elements of M, K, and C and use in Lagrange equations. And then you have to know whether it's 1 degree or 2 degrees of freedom so that you can differentiate with respect to the generalized coordinates. That's all for this lecture. Thank you.